So Einstein came up with E equals mc squared based on sort of his postulates of relativity and based on the things like length contraction and time dilation. He put all that together, and one thing that came out of that was this E equals mc squared, which is an interesting idea, right? It's basically relating energy and mass. And hopefully by now you've thought a little bit about what mass is and energy are, and we have some idea that mass is more of a property of things with energy as opposed to the amount of matter in an object. So it's sort of a measure of energy in an object. But one thing that we have to consider when we're looking at E equals mc squared, this equation that we're so used to and maybe we've used to calculate stuff before, is that we know, relatively speaking, according to relativity, mass changes depending on how fast an object is moving in a reference frame, right? So mass seems to increase in a reference frame as the object speeds up. So because of that, we need sort of a better version of this E equals mc squared. This E equals mc squared works very well when the object is at rest. So in fact, we sometimes call this the rest energy of an object. So I'm actually going to erase this, and I'll put E with a little subscript rest. The rest energy of an object is equal to mass times c squared. But we also know from the previous lesson that the relativistic mass, or the mass of a moving object, is equal to this gamma factor times its stationary mass, right? So if that's the case, can't we just substitute that in to this equation for the mass? Because the mass that we want to get is the relativistic mass, right? So we can, and if we get that, we get that the energy is equal to, and this is the energy sort of in motion, our relativistic energy, is equal to gamma times the stationary mass times c squared. So this is actually a better equation for energy. It sort of takes into account all the relativistic energy of that object. And that's the equation we use. Now, you'll notice I use different subscripts here. Instead of moving for m, we usually call this the total energy of an object. And when we're just calculating the rest energy, we just use mc squared, right, which is what it says down here. So the total energy is equal to gamma times the rest energy, or gamma times mc squared, where m is the rest mass. So the mass of an object if it was sitting still, okay? So let's do an actual example. And I'm actually going to change this example. I'll change it for you when I give you the handout, but on here I'm going to change it, instead of 1 million meters per second, I'm going to change it to 100 million meters per second. So we're moving at basically a third of the speed of light. It just makes the conclusions in the question come out a little bit clearer. So how much energy does this spacecraft contain while at rest? Well, we know the rest energy is just equal to mc squared, right? E equals mc squared, there it is. So the mass is 12,000. The speed of light is 3 times 10 to the 8 squared. Don't forget to square the speed of light. Very easy mistake to make is to forget it. I always forget to square that. And when we do that, we get that the energy, the rest energy, is 1.08 times 10 to the 21 joules. So that's a lot of energy. And remember, what that energy represents, it's the energy in all of the makeup of that spacecraft, right? So all of the mass of the spacecraft contains that much energy. So that's good for the rest mass. Can we find now the relativistic mass, or the total mass? So we know that that's going to be, and we'll call that the total mass. Sorry, the total energy. I keep saying mass. The total energy is going to be gamma times the rest energy, or gamma times mc squared. It doesn't matter. It's up to you. But we already calculated the rest energy, so we can just use the same calculation. So we do need to know gamma. Gamma in this question, well, we can calculate, is 1 over the square root of 1 minus 1 times 10 to the 8th over 3 times 10 to the 8th, and I got to square those things. Don't forget always to square. Don't forget to square. It's easy to forget. So if you do that calculation, you get 1.06. I'll carry a few more extra decimal places here just to make sure we're good. 1.0607 for the gamma factor. So when we plug that into our energy, our total energy equation, it's just going to be that times our rest energy, which is times 1.08 times 10 to the 21. If you're smart, you don't need to plug in the 10 to the 21 part, because 1 times 1 is going to be, it's still going to be 10 to the 21. That part's not going to change. So we end up getting 1.14 or 15 to 2 significant digits, or 3 significant digits, 1.15 times 10 to the 21 joules. So a little bit more, not a lot more, right? A little bit more. And in fact, 6%, about 6% more, right? Because that's what our gamma factor tells us. It's like increasing it by the energy by about 6%. So a little bit more energy due to the fact that it's moving. So this is the total energy. And the next question we could ask is, how much more energy is this compared to this? And we actually have a special name for that. Because it's the difference due to the speed, that's going to essentially be the kinetic energy, right, of this spacecraft, right? So the expression that we have, it's written down at the bottom of the page. The total energy of an object is the rest energy plus this little bit of extra energy due to the speed, the kinetic energy, right? So in order to find that kinetic energy, we could simplify this, or we can rearrange this equation. The kinetic energy is going to equal the total energy minus the rest energy, right? Now, another form of this equation that you might see some places is we can just plug in everything we know for these two things. Like we can plug in, we know that the total energy is going to be gamma times mc squared, and the rest energy is just mc squared, right? So we can actually simplify this equation, and we can actually, there's both terms have an mc squared, we can factor out an mc squared, and we can rewrite this as the kinetic energy is equal to mc squared gamma minus 1, right? That's just another version, it's a simplified version of this equation with just mc and gamma, right, which we all have calculated. And the thing is, I rounded both of these answers, so if we use this one, we might get less rounding error. So let's try it. Let's throw in what we know here and see what we get. So we get, according to my calculation, we get 6.56 times 10 to the 19 joules. Still a big number, 10 to the 19 joules, but it's 100 times smaller than the rest energy of this object. And 100 times smaller is not that much smaller. In most cases, when we're traveling very low compared to the speed of light, that's going to be much smaller percent than 6%. It was about 6% here. So it's about 6% of this total energy is this energy here. Usually it's going to be a lot less than that, but just because we're moving so fast, a third of the speed of light. So most of the energy in this is from the rest energy, right, from the mass. And then there's this little bit of extra energy here due to the kinetic energy. One other question you might have is, this isn't how we calculate kinetic energy. Don't we have another equation for kinetic energy? Well, we do. Our kinetic energy equation is 1/2 mv squared, right? And we've been using that since grade 11 physics, right? So if we use that equation, are we going to get the same number? Are we going to get a different number, lower number, higher number? I want you to pause the video here, make a prediction in your head. What do you think? It's going to be the same, higher, lower? Make a prediction, pause the video here, see what you get. So you should have gotten 6.00 times 10 to the 19 joules. So it came out less than this, but not much less. Does that make sense? Well, it does, because remember, as things move faster and faster and faster, we know that their mass increases from an outside perspective. So it would make sense, if this is getting bigger as the object moved faster, that the energy would be bigger in a relativistic sense than a rest sense. So it does make sense. So basically, these two calculations are for two different things. This is the relativistic kinetic energy, and this is the non-relativistic, or the rest kinetic energy. It sounds funny because kinetic energy means moving, but that's assuming that our mass doesn't change and isn't affected by relativity. So there we go. It makes sense that it's coming out less. Okay, so here we go with another question. With a single electron this time, we're accelerating it to 95% the speed of light in a particle accelerator. So clearly here we are at relativistic speed, so we should definitely be using our relativity equations as opposed to our non-relativistic equations, our Newtonian equations. So we need to calculate the total energy and kinetic energy of the electron. Well, we know our total energy, this thing is definitely not at rest, so our total energy is going to follow the formula gamma times mc squared, right? Because gamma is not going to be 1 in this case. It is moving. Gamma is 1 only when it's stationary. So do we know the mass? We do know the mass. Do we know the speed of light? We know the speed of light. Do we know gamma? Well, we can calculate gamma, 95% the speed of light. And if we do that, gamma should come out too. I'll let you calculate it yourself, but what I get is 3.2026. Carrying a few extra decimals here, again, just to make sure our final answers are accurate. So the total energy is just going to be equal to gamma, which is 3.2026, times the mass of an electron, which I put it on your formula sheet. It's 9.11 times 10 to the negative 31 kilograms, times c squared, 3 times 10 to the 8. Squared. I always forget to square that. When you do that calculation, the total energy comes out to 2.63 times 10 to the negative 13 joules of energy. Okay, so it's a small number because, I mean, it's the energy of a single electron, so it's obviously not going to be a big number. But remember, this is the total energy. It's made up of the rest energy and the kinetic energy. So can we calculate the kinetic energy? And the relativistic kinetic energy, remember, is just going to be the total energy, the total energy minus the rest energy. We've already calculated the total energy, so we just need to subtract from that the rest energy, which is mc squared. Let's just off to the side calculate the rest energy, just so we can compare all three of these values. So the rest energy comes out to, when we plug in our mass, which is 9.11 times 10 to the negative 31, times c squared, which is, by the way, if you remember that c squared, like c is 3 times 10 to the 8, c squared is going to be 9 times 10 to the power of 16. You don't have to plug in, you don't have to actually square it each time. You can just plug in 9 times 10 to the 16. Makes it easier for calculations. And if you do that calculation, the rest energy comes out to 8.20 times 10 to the negative 14 joules. So the rest energy is actually like a small chunk of this, right? It's not a huge chunk. It's not more than half of it, right? It's a small chunk of it. So to calculate the kinetic energy, all we need to do is subtract this minus this, right? And we should get our kinetic energy. And if we do that, what we get is 1.81 times 10 to the negative 13 joules. So there we go. Notice how, in this case, the kinetic energy is actually a much bigger proportion of the total energy. And that's because the closer we get to this speed of light, the higher proportion of that kinetic energy, of the energy, is going to be kinetic energy. Because remember, the rest energy isn't changing, right? That's just mc squared. So it makes sense. The last thing about this question is we've usually been using our energy as in units of joules. But when we're looking at stuff that's small, made up of individual charges or small groups of charges, there's actually another unit of energy that's pretty convenient, and it's called the electron volt. And I made a little note at the bottom of the page. 1 electron volt, it's basically the energy of a single electron, the energy that a single electron has, in a 1 volt field. So if you think about it this way, 1 electron volt, it's like you're multiplying 1 volt times the charge of an electron. right? And remember, a volt is like saying a joule per coulomb. And the units here, think about it, 1 volt is a joule per coulomb, and the charge of an electron is in coulombs, right? So these coulombs are going to cancel out. So multiplying electric potential difference times charge gives us a unit of energy. So we just call this, specifically when it's the charge of an electron, we call it an electron volt, small e, big V. And it's just a convenient unit to use when we're dealing with very small things, single charges and stuff like that. If you look at particle accelerators, they usually report energies in electron volts or mega electron volts, which is 1,000,000 electron volts. So in this case, let's try converting all of these energies to electron volts, just to get a bit of a sense for it. So the total energy was 2.63 times 10 to the negative 13 joules. 2.63 times 10 to the, what was it, negative 13 joules. So to convert that to electron volts, 1 electron volt is equal to 1.6 times to the negative 10 to the negative 19 joules. So to cancel out, we would need to divide, right? 1 electron volt is equal to 1.60 times 10 to the negative 19 joules to make those joules cancel out. So all we got to do is divide 2.63 times 10 to the negative 13 divided by 1.6 times 10 to the negative 19. That gives us 643,750 electron volts. Now, because there are so many of them, we could do it in scientific notation, but because this is in millions of electron volts, what we can say is this is a mega electron volt. So a mega electron volt, MeV, is equal to 1,000,000 electron volts. So mega is just the prefix for million. I always remember it because they both start with M, right? So 1 mega electron volt is 1,000,000. So I can just say that this is 1.6 mega electron volts. So 1.6 is a nice number to use, right? It's much easier than saying 2.63 times 10 to the negative 13 joules. So when we have questions like this, that might be a convenient unit to use. So let's see what the other ones come out to be. Like, what's the rest energy come out to be if we convert that? It comes out to 0.51. We'll do 0.51 mega electron volts. Okay, so that makes sense, right? It's a small portion of this total. And then we can lastly do the kinetic energy. The kinetic energy. Hold on. EK. In terms of mega electron volts, what does it come out to be? Again, you can pause the video here, try it yourself, see if you get the right answer. That comes out to 1.1 mega electron volts. So clearly, these three numbers, for the three energies, the total energy, the kinetic energy, and the rest energy, those are much easier to deal with than all that scientific notation. So when it's a question like this, I would recommend putting them into these units here. There we go.